And this function is the uniform distribution function, and probably the simplest one in the list, because here each value between a lower and upper bound are equally likely. So the parameters are indeed a minimum and a maximum, and between them each possible value will have an equal chance of occurring. Some examples are flipping a coin, which will be 50-50, throwing a fair die, either from 1 to 6 or whatever die you have, but also guessing a number from 1 to 10. However, here there is a bit of a deviation, because if you ask people to guess a number between 1 and 10, people tend to have a preference of certain numbers over others. But that aside, if you look at the distribution function, then we see that the theoretical curve is just a straight block, because each value between 0 and 1, the minimum and maximum value, the parameters of this distribution, has an equal chance of occurring. Of course, because we are working with a random sample of just 150 sample points, the corresponding histogram will only approximate this curve. So sometimes it will be larger and sometimes it will be lower. And now let's look at our CDF. In this case, for the uniform distribution, we see that our cumulative distribution function is a straight line. Now this can be understood by thinking about the heuristic that I said in the previous slide, namely that the slope of the CDF indicates where the majority of the data falls. Now, because the slope of a straight line is everywhere exactly the same, this reflects the fact that for the uniform distribution function, each value occurs equally likely. Now, in our scenario, because we chose the minimum and the maximum parameter to be 0 and 1 respectively, the 60% data interval, and in fact all of the percentiles, will map 1-to-1 to the actual values. We see that for the 80th and the 20th percentiles, the values map exactly to 0.8 and 0.2. But if you look closely, this 20th percentile doesn't map exactly to 0.2. And that has to do with the fact that these intervals are based not on the theoretical curve, but on the empirical curve, on the generated data. And we see that this light blue line represents the CDF of the generated dataset. If we hop over to our code, then we will see how easily it is to generate these functions. For the uniform distribution, we have to define two parameters, a low one and a high one, which are the lower and upper bound. Then we just create a new Python array, uniform distribution, numpy.random.uniform. We provide the parameters, and the size will again be this 150. Now we can, of course, just take a brief look at where we plot this. And let's go over it very briefly, because this is all very familiar code, and I go into the details anyway in these separate videos on the YouTube channel. So first, we plot the histogram, and the histogram just requires our Python array and the number of bins and the other parameters. And in the next 3 lines, the theoretical probability distribution function curve is created. Then we give this a title, the uniform distribution, which then holds the probability density function and the histogram. And then in these lines, we create the cumulative distribution function. Here we create the empirical cumulative distribution function based on the generated sample. And here we create the theoretical CDF with the same X that we used for the PDF. Then this is again this function that shades in the areas and puts the lines on the cumulative distribution function, and we give it a name. And so if we run this cell and we scroll down, then we see indeed that this is the row where the uniform distribution function is visualized. And at this point, let's just for fun, increase the sample size. Let's indeed put it to 150,000. And let's see what happens. Of course, it will need to think a bit longer, but then we see that indeed the histogram is also very flat and very much approximates the underlying distribution function. But also the cumulative distribution function now overlaps perfectly with the theoretical alternative. So let's now go back to the slides and look at the following function.